Imagine searching for a phrase across 1 trillion tokens in under a second, while capturing not just exact matches but semantic variations, synonyms, and paraphrases. Traditional exact match algorithms break down at this scale, and naive semantic search creates an exponential explosion of candidates that's computationally intractable. Let's start by understanding why existing search methods fall short at trillion scale. Building on that challenge, traditional exact matching tools like suffix arrays completely miss semantically similar phrases. Meanwhile, inverted indexes struggle with the sheer scale of modern language model training corpora, and attempting to relax search semantically without careful design creates an exponential explosion of candidate matches that's impossible to process efficiently. The authors introduce a clever solution that exploits fundamental statistical properties of language. The algorithm introduces 2 synergistic innovations. First, a disk-aware staged suffix array architecture uses a sparse RAM-resident index to localize searches, ensuring each lookup requires only a single random disk access. Second, dynamic corpus-aware pruning exploits Zipf and power law distributions in natural language, iteratively filtering candidate expansions against actual corpus occurrences to suppress exponential growth. This visualization illustrates the pruning mechanism in action. When searching for Olympics gold medal, naive semantic expansion would require exploring the entire gray stripe zone plus the blue zone. The dynamic pruning strategy eliminates the gray regions by checking corpus occurrence at each expansion step, dramatically constraining the search space while preserving semantically relevant matches. The empirical validation demonstrates remarkable efficiency at unprecedented scale. Connecting these innovations to real-world performance, the authors evaluated SoftMatcha 2 on diverse corpora spanning up to 1.4 trillion tokens. They achieved 95th percentile soft search latencies under 0.3 seconds, with exact search running 33 times faster than the infinigram baseline. And critically, latency remained nearly constant even as corpus size increased by orders of magnitude. Beyond raw performance, the authors applied SoftMatcha 2 to benchmark contamination detection, uncovering dirty test samples overlooked by exact matching. Of the newly identified samples, 81% were validated as true contamination involving semantic paraphrases or template variations like number substitutions, demonstrating that soft matching is essential for maintaining benchmark integrity in the age of trillion-token training corpora. This breakdown reveals the contamination detection results across multiple benchmark datasets. The stacked bars show how many dirty problems were flagged, with the critical insight being the proportion of samples uniquely detected by soft search that were invisible to exact matching, validating the necessity of semantic flexibility for rigorous data curation. In Central Europe, SoftMatcha 2 establishes a new frontier for semantic corpus search, proving that trillion-scale soft matching is not only possible but practical, with profound implications for training data analysis, contamination detection, and understanding the behaviors of modern language models. To dive deeper into this work and explore other cutting-edge research, visit emergentmind.com.